3.5 Part 2. So we left off last time looking at 54 times 53 times 52 equaling that 148,824 ways that a 54-person race could have, first, second, and third place finishes. All the different ways that you could have first, second, and third place assigned to all those different people. So a better way to do this, instead of the way we just seen, requires the use of factorials. So what is a factorial? Well, let's take a look at this here. 8 with what looks like an exclamation point. And in English, you would be correct. That's an exclamation point. In math, it's no longer an exclamation point. This is the factorial symbol. So this is not 8. This is 8 factorial. Oops, I need to spell symbol. Oh, I was doing that right, sorry. Sometimes my spelling is questionable. All right, so the factorial symbol, exclamation point in English, but in math, you always would read this as 8 factorial. And what it means is that you're going to do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You always stop at 1, because if you go to 0, then 0 times everything else is going to zero it out, and you don't want that. So you just count down till you get to 1, counting down by whole numbers, and then you stop, and then you multiply everything together. And if you were to do this in the calculator, you would get 40,320. So there's different buttons for this on different calculators. I'm not going to go through those, but I will show you in Desmos how to do this. So in Desmos here, you would just type in 8 factorial, and there's that 40,320. All right, so you might be saying, but wait, 54 times 53 times 52 just stops at 52. It doesn't go all the way down to 1. So how can we use factorials to write a formula for permutations? And what we're going to do is actually use more than one factorial to make this happen. So up top, I'm going to have 54 factorial, because we are starting with 54 people in the race. Down below, I'm going to use 51 factorial. There were 3 finishes. 54 minus 3 is 51. We're going to see that's a common thing with these permutations. And why is this helpful for us? Well, if we list this out, 54 times 53 times 52 times 51 times 50, and then all the way down to 3 times 2 times 1, and we put that over, the expansion for 51 factorial is 51 times 50 times all the way down to 3 times 2 times 1. And if you start canceling the common factors of the numerator and denominator, you see that the 51s go away, the 50s go away, all this stuff in between goes away, the 3, the 2, the 1, all cancels out, and you're left with that 54 times 53 times 52, which is equal to that 148,824, 148,824. So the key to this, in order to get that correct denominator, is to note that 51 does equal the total number of people in the race minus the number of places that we were interested in. So the total minus those being chosen. The chosen ones get first, second, and third. And that's where the permutation formula comes in. So permutation is an arrangement of a set of items. Arrangement, that's where the order matters. And the number of permutations of n items taking r at a time is given by, they use this p of n comma r, which equals n factorial, the total factorial, over n minus r. So that's a 54 minus 3 that we used in the race example. And then you do that in parentheses first to get a number, and then you take that number factorial. So it's basically like what we did right here, where you got the 54 factorial over 51 factorial. We did the subtraction and then applied that. And another way that's more common in calculators is this, where you have the NCR written that way. So when you see it in a calculator, you'll see, or I'm sorry, not NCR, getting ahead of myself, NPR, you'll see that in calculators. And you usually will have to enter in the N first, then NPR, and then the R number second when you're doing this in a calculator. But over in old Desmos, let's go ahead and do that race example. So in Desmos, you come down here and show the keypad, go over to functions, go to stats, and then you have NCR, which we will see in this class, and then you have NPR right here. So you hit the NPR, and this one, it's not like a lot of TIs, they have you enter N, then NPR, then the R. Here they have you enter in the N, so 54 was the total number of people in the race, and then comma, the number that are being chosen. So we're wanting first, second, third place, so 3 people are being chosen for those top finishers. And then you can see you get 148,824 as your answer. So just use the functions, stats, NPR, N comma R in the entry for the command. All right, so then the keys to this: order matters. Can't stress this enough. This is when order is important. First place is a much different place than second and third in a lot of people's minds. So the order in which you finish the race is important, especially if there's prize money on the line. So order matters in permutations. Each object is distinct. Talked about this, but just to reinforce it, each object is distinct. No 2 items are the same. So another example here. A club has 23 people in it. How many ways can a president, vice president, and secretary be selected or elected? With what we're going to see shortly here in combinations, there's a lot of similarity between permutations and combinations. And sometimes the problems will be thrown at you out of order, and you have to know which is which. How do I determine if it's permutation? How do I determine if it's combination? And when you're looking to determine if it's a permutation, you ask yourself, is order important in this scenario? And in this case, named positions will always indicate order matters. Order is important. Because again, 2 different people are going to run that presidency a little differently, or maybe the secretary differently. So order matters with named positions. So that tells me it's a permutation. And this isn't so important now because this is always seen, but as I say, as soon as we get to combinations, you're going to need to be able to tell the difference. And the main difference, the only real difference, is that order matters with a permutation. So in this case, there are 3 people being selected out of the 23. So N is 23, R is 3, and we're going to have 23P3. And when you go over to old Desmos and type this in, I think I can just do it this way, NPR, yeah, good, 23, 3, you get 10,626 different ways that little group can have presidency, vice presidency, and secretary selected. Pretty crazy that there's that many in such a small group, but that's how many there are. Right, so how many ways can 8 books be rearranged on a shelf? This is also a permutation. And technically, you could do 8 factorial, 8 times 7 times 6, as you put them in order on a shelf, you have one less book to work with. But if we use a permutation, the n is 8, the r is also 8. We're choosing all 8 to put on the shelf. So it would be 8p8. And when you work that out, you get 40,320. Again, these numbers get very large very fast, and it's kind of surprising that there's actually 40,000 different ways to rearrange those 8 few books on your shelf. Whew, crazy. But that's what it is. All right, so combinations, it's basically the end of permutations. That's all there is to it, as long as you identify that there is order important. Rearranging books on a shelf, the order of the books is important. Picking president, vice president, secretary, that's important. First, second, third place, again, order is important there. So, order is important in all those scenarios. Permutation. Combinations are similar to permutations, as I've mentioned, but order does not matter. So when would this be useful? When is order not really all that important when you're selecting things? Well, if 3 people are selected for a Hawaiian vacation, does it matter if you're the first, second, or third person chosen? No. I don't care. As long as I'm going to Hawaii, that's all that really matters. So each is going to Hawaii, whether first, second, or third. So in this case, order wouldn't matter. You don't care if you're the first person, second person, third person. You're going to Hawaii, and you're probably, unless you just for some reason have something against Hawaii, you're probably very happy about that. All right, so how is the formula different? And I think for what I'm going to do here, I don't know that I'll have enough time in what's remaining on this video. So we'll see how this formula differs in part 3.